Good afternoon, everyone. Anyway, today we'll talk about the initial stage of aerodynamics for atmospheric flight. There's been a slight change to the work division between aerodynamics. Radius will now take over every phases related to ground effect operation, in such as takeoff, landing, and ground cruise. And then the contribution for different advices will go towards the wing platform design. Because when we try to optimize the wing, we don't want to just perform well in the cruise, but as well as considering the other parts of the mission profile. So the outline of today starts with the method we use in constraint diagram. It's basically Raymond's approach, and then we try to determine the design point from there. One thing Yix brought forward just now is we can try to adjust the design point. Maybe we could, I don't know whether we do it at the end to see whether actually the real plane can actually change, incorporate the design point we have decided, or actually the plane actually doesn't fly at all. So we don't know. Because when we change something, it seems like the whole wing is changed, every integration has to be changed, structure has to be changed. So it's a very, very big deal. And when we move on to wing design with some basic initial stage steps. So the constraint diagram, first, constraint diagram is being performed by the aero team to try to estimate the reference wing area for the average loading. There's some presettings we need to input for the Raymer relations to work, and we've chosen aspect ratio of 4, the wetted area ratio of 3.5, a skin coefficient for a typical prop seaplane, and turbofan efficiency 85%. That allows us to get the data from here for the zero lift drag and estimation, and as the Oswald efficiency and the induced drag factor. I think these values can actually vary after we try to design the plane afterwards, and then maybe that's the iteration we can go towards iterating the constraint diagram. The phases we consider follows the order of the mission profile. The takeoff on ground, the climb is divided into two segments. OEI stands for one engine operative, and the EO stands for all engine operative. The segment 2 was without the OEI. The reason being is because if OEI happens in that stage, it's very likely to abort the flight already and back to the ground. So we do not continue our mission towards the next stage. The turn is tested at an altitude of 1 kilometer, assuming we do turnover after takeoff to head towards the direction we want, and at a fairly low G maneuver of 30 degrees row. The cruise takes care of the level and ground at the specific Mach number we defined as 0.45 to 0.2, and the approach is divided in the same way similar to climb, but with negative climb rate towards the ground. So it's OEI and AU again. Similar for segment 2 as well. If OEI happens, it's very likely we abort the flight anyway. So we try to land on sea somehow. So landing on ground. The Raymer's top approach, we try to incorporate Roscombe approach to the takeoff requirement. But the result, we get the wing loading is very, very low, and we get very, very high reference wing area, and we think it's not very realistic in our approach. But one thing Roscombe mentioned is the 2,500 feet military requirement for the transport vehicle. So we thought might as well take this into account for the most critical, the most maximum requirement we may actually need. The VSOR is predefined because we want to minimize the impact load onto the sea landing with the landing flap configurations with 5 meters per second lower than the takeoff flaps configuration. The MELS, that's the error, it should be less than with all the shown climbing. And the power lift rate has been changed from the initial concept of just raise to the power of density ratio of 0.7. We now change the function of in terms of the free stream Mach number. And the landing distance, there's not much restriction on the landing distance, so we thought a 2 km rubble should be reasonable for this to fly back and then land safely. So that's the overall constraint diagram. This is the design point we've chosen. This is the allowable region in here. These are design point. We have decided a wing loading of 2,000 Newton per meter square and a power to weight ratio of 22. This gives a reference wing area of 92 meters per second, meter square based on the maximum takeoff weight. Moving on to airfoil selection. This is the initial stage where we do not confirm our selection in airfoil. The only trade-off studies we always need to bear in mind is hydrogen and hydrogen performance. This includes enough whether we have enough lift and during takeoff and landing, and the opposite needs that submersible phase they will need. They actually want minimum camber and minimum thickness to reduce the wetted area and the frontal area when they try to have some drag reduction solutions, and as well as For stability, they actually want symmetrical airfoil for that underwater control, and a smaller CM since we already got a quite high pitch down movement from the engine top mounted during flight. The potential volumetric issues comes from the fuel capacity, the structural integrity, and actuator of flaps. We have not decided what high lift devices we are going to choose based on that, but it's very likely to be plane flaps so that we can achieve a negative deflection for a downforce if it's needed in any phase during the submersible flight. We've started with initial choice of NACA airfoils because they're the most easy to access. We've tried to get the values from your wing section by measuring. This is the wrong one, we will read the wrong scale. It's actually minus 0.1 for all three airfoils, but that doesn't affect the next step of collocation method when we try to use. The characteristic we use implied in collocation method include a zero lift angle of attack and the lift curve slope in radians form. The three airfoils we've chosen they look like this without any scaling or anything. We can see there's a significant rear camber on the NACA 642-415. This is modified for high speed flow with laminar flow modified airfoil for the specific range they have. So they have much higher drag when they're outside the optimum design range. So it may be a problem when we try to incorporate this kind of airfoil, and it's more likely for higher speed as well. So our Mach 0.45 is, we need to research further into the airfoil. 23015 is an older airfoil that hasn't been modified on laminar, and 2415, the 4-digit series, is most likely to see on plane, although it's most likely to be symmetrical airfoil, which is slightly cambered. We try to use the lift characteristic and put it in the collocation method. When we try to do it in Excel, we only do a 2x2 matrix, but in the MATLAB code, we can directly import the main code. When we try to do, it's a modified version of the AVD code we do for aero, but just for the geometry section. So after we input the wing area, the taper ratio, it outputs the reference wing area, the tip chord, and the root chord, and that allows the collocation method code to input the data. And then in the first stage, we assume linear twist and chord distributions. Just for simplicity, we can actually code in much more complicated lines of code just for improving trying to get the elliptic loading we want. It's capable for a range of alpha. I spent some time yesterday to modify the code because we previously can only apply one alpha angle of attack in there, and it only gives you one CL. And we try to use the collocation method to give us a rough idea of the CL curve, how it's going to look like, based on purely potential flow and the single bound vortex theory. The advantage is, as I mentioned, we can go not high dimension definition, but high dimensional matrix operation. Currently, I've chosen a 49 to 49 matrix, so we take from A1 to A99, omitting all the even numbers for symmetrical flight, symmetrical plane. Computation efficiency is quite high. We only run for 0.5 seconds. This gives us the answer. The introduction of flaps can still be incorporated, similar to the past paper questions. Where we get ideas from, we can get a level we want, and that follows to the freedom on wing geometry. As I mentioned, we can twist around with the twist and the chord. The elliptic factor, when you try to rearrange the lifting line theory, we can get an elliptic factor. The closer it to 1, the closer we are in the potential flow, closer to elliptic loading for the wing. The chord variation just gives us a sanity check to see whether our chord distribution is kind of wrong to what we expected. And this is currently for the current setting of a span of about 8 meters semi-span and the root chord 6 meters with a bit more. So the iteration stops actually for different aircraft when we try to reach our design CL. The current CL design is 0.27. So iteration stops when we try to change around with the root sector angle and the twist from the root to tip. And they're all fixed with one taper ratio. Of course, we can do much more iteration with different taper ratios, and that can be a beneficial advantage for structural consideration for the fuel capacity and the bending moment consideration. But for the time being, we just optimize the twist, the linear twist, and the root sector angle such that we get 0.27. So first we substitute a range of reasonable angle of attack within the stall angle of attack shown in field wing section. We've tried from -3 to 8. On the CL curve, we're trying to plot it. We can see that they're all three slightly performing just with very small deviation and very high angle of attack. But roughly, in basic condition, they all can reach the 0.27 criteria we have. The CL to CDI curve is not the usual curve we use for comparing lift to drag. It should actually be CL to CD naught, but for the collocation method, we just directly get the output and try to modify it. We can see there's a slight increase in L to DI induced drag ratio on the 642 to 415. I think the reason is the combination of zero lift angle of attack and the lift curve slope quite falls into better performance than the other two non-modified airfoil, because the 4 stands for 0.4 CL optimization within a range of 0.2, so it's plus or minus, so it's within the range of 0.2 to 0.6. And lastly, the elliptic error factor, I've tried to minus 1 from it and change it back to percentage. We can see for NACA 642415, we get a 3% error from the elliptic loading based on the 49 by 49 coefficient matrix. We can go further. I've tried to convert the answer. It only changes by an order of magnitude of 10 to the minus 5 when we change the induced drag, or we try to upgrade it to 100 or 200. It changes very slightly, but when I increase the matrix size, it actually changes a little bit by little bit. So this is collocation method we've done, an upcoming plan for next week. For tomorrow, the 3 airfoil selections is temporarily as a starting point to see the different characteristics of the 3 choices we've chosen, and then pick out the benefit features from them, and try to refine the choices of airfoil by tomorrow so that everyone can start working and give them more refined wing geometry and wing loading to work on. The wing design, we plan to use the Vortex-Classics method and 3D panels we mentioned last week. The Vortex-Classics method, we try to look into 2 different programs, Tornado and XFLR5. The second program uses X4, and yesterday we tried to do with the other member. The X4 only gives reasonable result in the lift curve slope, but doesn't do very well on the other parameters, except CM as well. And lastly, the overall body design, we want to do the drag reduction on after we have finished the wing design, such as coating on the aircraft or any riblets we can apply. And this is all from Aero this week. Q&A time.
How did you arrive at a skin friction coefficient? And how can we possibly say that the skin friction coefficient is constant all over the aircraft?
When we try to follow Raymer's approach, they have a table of results for the C popping.
Okay, but if we think about this, there's no way the skin friction coefficient is going to be constant across the whole airfoil, right? So can we do better than come up with just we plug some skin friction coefficient out for now?
We can do the boundary layer analysis.
Yes,
like
that's what I'm guessing.
Yeah, but we haven't. We try to follow because we have very time limit. When we try to, after last week's presentation, we spent Friday and Monday try to finish the constraint diagram, and then we try to move on to our own stuff. So our time is kind of like concept because we spend the weekend researching on the further steps as well. Maybe after the iteration of constraint diagram, we'll try to change the CD naught, E, and K1 and CF. Although every parameter can be changed, so it's like all correlated by that. It's very easy to change. So maybe they would change the ranges.
I'd like to see more detail. I mean, I think just saying that our skin friction coefficient on the plane is this, and it needs to be defined.
This is just an initial mean CF for the entire aircraft of this type.
How important do you think
Out there, yes.
skin friction is in all the sources of drag you have?
For the timing, we haven't considered submersible and sea landing onto the constraint diagram.
So during your phase?
Yeah, during our phase. The CF, we're going to see much higher Reynolds number during the cruise, and I think the skin thickness, the skin friction coefficient contribute quite a lot to the CD naught that we're hoping for in comparison to the other phases. So I think it's a good idea to actually have a more refined model on the boundary layer on both the wing, the nose, and all the nacelle and every exposed surface area. But for the time being, we want to concentrate doing the wing first, and then we can refine on the other parts of the body of the aircraft. That's our plan.
So were you attempting to get an lifting distribution by playing with a twist? Is that what you were trying to do?
Yeah. For the time being.
Okay. And your error is compared to CL squared on high aspect ratio, is it? Is that what you're plotting on the last graph?
Yeah. So this factor comes from the formula by taking out the A1 square and then change it back to CL square over pi AR. And this is the thing you're left over with, times it by the model elliptic CDI.
On this, actually, did you consider whether you could actually optimize both aerodynamics and minimize weight by playing around with any other parameters?
The
Not
taper
all
ratio is
just
one of the things we should actually iterate quite a lot for reducing the bending moment requirement. If we can actually reduce the tip chord, and one of the things I forgot to mention is the airfoil selection refinement. One of the proposed ideas was to use the same series of airfoil with different thickness around the chord, the midspan of the wing and the tip, and then we can try to reduce the bending moment arise from the tip and then concentrate more on the construction to the root, so it's more inside the fuselage and above the CG.
Are they all 15% thick?
Yeah, for this initial trial. Yeah.
So why have you chosen that number?
It's a circulation thing. We want to ask the system people how much fuel they actually want to fit into the wing box, and then they said they need to ask the proportion to see the volume of the fuel, because they need to calculate how much fuel they actually need to use. And then they arrive at, are they still calculating the mass flow that affects the fuel consumption? So we thought we may actually just pick a starting point for the time being, allow time for them to do that work, but meanwhile we don't stop for anything. But at least we can have an airfoil to demonstrate.
So you
that.
think this is going to be
It's going to
a
reduce.
compromise between fuel capacity and aerodynamics, not structures and aerodynamics?
It's a combination of all three, both aero, structure and fuel capacity. We need to get a minimum bound on the thickness to chord ratio based on these three factors. Because we're not flying transonic or any flight. The thickness should be less critical than the transonic regime.
Looking at your chord variation, is that actually your plan form?
No,
Okay.
that's just a chord.
That's just cool.
We plan to use zero swept angle for the chord point line. So we actually not a big sweep forward, but we try to, that's just the chord distribution.
So the taper's accurate, is it?
The taper is accurate for 0.5. But it doesn't look like the wing we need to look for. We want to actually reduce the zero for the swept, so such that we don't get any span-wise flow for the boundary layer.
No end plates.
End plates. You see, the end plate is a big problem for the sea landing. But see whether they actually want pontoons on the side of the hulls or do they actually want on the wingtip. If they actually put a pontoons on underneath the wing, it acts as partial winglets, but it's not a very good idea for the cruise phase. When we try to put winglets bend towards the not the suction surface, but the lower surface is not as efficient as putting the winglet to go up and then try to block the lower pressure air to go under to the high pressure. And for the high pressure air to come over to the lower pressure region. And the split one is not very well. We'll have to research it. But that's where they want to put pontoons on, and then we need to figure out. So for the time, we just decide based on the reference weight, and we try to modify it afterwards. Otherwise, we have nothing to show. Even though you have the best cook in the world, you have nothing to show. So we have to. The code has been checked, so we use a past paper question to check, so everyone cooks exactly the same value and come up the same answer. But unluckily, the question hasn't came out this year, so maybe it's a good practice.
If you can go back to where you talked about the power lapse rate real quick. So you assume that there's no effective altitude on the power?
I think we should actually incorporate this, but after I think Roshan can comment this.
Well, the equation had both Mach number and the density ratio. The expression for the lapse rates had both Mach number and density ratio in it. Yeah.
So I only saw the Mach.
Yeah, I'm getting the code up.
Are there any more questions?